In order to analyze an IR spectrum, we need to be familiar with the various regions in an IR spectrum. Remember, an IR spectrum is upside down. The signals come down like this. And the spectrum is arranged according to bond stiffness. The stiffest bonds show up over here. The least stiff bonds show up over here. The least stiff bonds are single bonds. So single bonds are going to show up over here. This is 1600 inverse centimeters. Here the edge is usually around 400 inverse centimeters. So between 400 and 1600 inverse centimeters we have the single bonds. Then between 1600 and 1850 we have the double bonds. Carbon-carbon double bonds, carbon-nitrogen double bonds, carbon-oxygen double bonds. Double bonds are stiffer than single bonds and therefore show up at a higher wave number. Between 1850 and 2100, there isn't a whole lot of activity. There are some signals that can show up in here when you have an aromatic ring. We call them aromatic overtones, or these little bumps that show up in here. And by analyzing those bumps, you can tell whether you have a monosubstituted aromatic ring or a disubstituted aromatic ring. But in general, unless you have an aromatic ring, this region is pretty much empty. Between 2100 and 2300, we have the region of triple bonds. These are even stiffer than double bonds. Carbon-carbon, carbon-nitrogen. We don't have carbon-oxygen triple bonds. Then between 2300 and 2700 is again another region that is fairly empty. And then finally, this is where all of the bonds to hydrogen show up, XH. Now, granted, this is a single bond. Any bonds to hydrogen are going to show up all the way on this region of the IR spectrum. And this region can be broken up as well. In this region here you have CHs that are just regular sp3 hybridized CHs. A carbon with 4 bonds and a hydrogen on it is going to show up to the right of this line, which is 3000. So usually this region right here between 2700 and 3000 is usually going to be pretty busy with signals because of all of the CHs that are usually present in organic compounds. Now, if you have a carbon-hydrogen bond where the carbon is sp2 hybridized, that's going to show up, that CH bond is going to show up right here to the left of 3000. And in fact, if you have a carbon atom that is sp hybridized, that CH bond is going to show up even further over here. And then you have NH and OH showing up way in over in this part of the spectrum. But here is where you have all of the bonds to hydrogen. Here's where you have your triple bonds, here's where you have your double bonds, here's where you have your single bonds. In general, the single bond region, this region between 400 and 1600, which we call the fingerprint region, this region is usually very, very busy with signals, and sometimes you can analyze a few of those signals and get information, like for instance a CO bond can generally be spotted in here, and a few other single bonds that you're going to find. But for the most part, the main focus of your analysis of an IR spectrum is going to need to be on the following region, which we call from 1600 and above, which we call the diagnostic region. You're looking specifically for double bonds, triple bonds, or any bonds to hydrogen. And generally what you're going to do is when you have an IR spectrum, the first thing you're going to do is draw a line at 1600 and draw a line at 3000. Ignore everything to the right of 1600 except for a few signals that you might be looking for, and then focus the rest of your attention on everything above 1600. Look for the double bonds, look for the triple bonds, then draw a line at 3000. Look for the CHs just to the right, which are your regular CHs from an sp3 hybridized carbon atom, but then also look to see if there's any CH bonds where the carbon atom is either sp2 or sp hybridized, as well as NH bonds and OH bonds. And this is the structure of an IR spectrum and the procedure you should follow when methodically analyzing an IR spectrum.